At the moment, you're getting heating in summer, but in winter, you're getting temperatures getting colder. So we're headed towards another glaciation.
My guest today is Dr. Stuart Arthur Harris, who is 92 years of age, does research in climatology and paleoclimatology, has published papers in about 7 different sciences, and who has published at least 2 climate papers this year.
I'm an emeritus professor in geography at the University of Calgary. I have spent something like 40 years looking at permafrost and working with Russians and Chinese on that. I was asked to come over by the Americans to work on it, and we got out a book about 2017, summarizing the work that had been done in the 3 countries, China, Russia, and Canada. In the process of doing that, we learned an awful lot about how heat travels through the surface or around the surface, where it comes from, and so on. And the permafrost, it depends really on the climate. It's basically the soil that has been affected by cold temperatures, but not completely covered in snow for most of the year. So that's my background. I have a presentation concerning what the ideas of connected with climate, how it works, and what to expect in the future, based on what we've learned about the past and how heat comes to the surface of the Earth. This is a talk about the proposed causes of climatic changes since World War II. We're going to compare them and indicate the differences and what most likely causes will be. During the mid-19th century, the German and French climatologists had made good maps classifying the range of climate based on exploration of most of the world. These are still in use. Adamar in France had outlined the Earth-Sun relationships, and these were further developed by Paul in a book in 1875. And these determined the range of insulation reaching the surface of the Earth. Climatologists were fairly satisfied with this, and they have made very little progress until about World War I, when a Serbian by the name Milankovic refined the calculation of the Earth's orbital movements relative to the Sun. The war in Europe emphasized the need for good climate data. They had to get a lot of new weather stations out, and you have to have 30 years of data before you've got a reasonable idea of what's going on. Since then, we've had new studies using revolutionary methods of instrumentation by oceanographers and environmental scientists. There's continuous monitoring of environmental factors, and we've also got satellite measurements. A fast-growing data bank that is accumulated using up-to-date methods that now have given us a better idea of what we're dealing with. This talk compares and contrasts the resulting theories that generally support themselves one another with one exception, and it represents a considerable advance on our understanding of climate change. Now, the sun supplies more than 99% of the total energy driving the world's climate. The shape of the Earth results in greater insulation at the Earth's surface in the middle of the Earth rather than the poles. That's because you've had parallel rays coming in and you're dealing with a curved surface. This sets up a considerable thermal gradient, which drives the ocean currents, the movement of the air masses, and the associated frontal systems to the air masses. Differences between day and night and seasons give you additional modifications. In order to understand what happens to that heat, we have to look at the surface. We find that 70% of the Earth's surface is occupied by water, together with only 30% consisting of land, which includes rock, soil, or ice. The albedo or reflectance of ice ranges from 0.5 to 0.7. So ice and snow cover surfaces reflect back into space much of the incoming radiation. This, of course, means that there's not as much heat absorbed at the surface of the Earth in the polar regions. Water has a very high heat capacity, so it can store or transport large amounts of heat energy. It's also translucent, and that's why it absorbs so much, because you're heating a thickness of water. It absorbs, as a result, about 5 times as much energy as soil. And wave action modifies the heat distribution because it takes the heat from the surface of the ocean and mixes it with colder water underneath. Transmission of solar energy into rock or soil is much less effective. It has to be by conduction. So that is the reason for the much greater absorption of heat. How does heat move around the surface? Well, dry air has low heat capacity, but moist air can carry quite a lot of heat in the form of water vapor, water droplets, or snow and hail. Actual water content in monsoons and hurricanes and rivers of water can be enormous. But in ordinary air, which is not saturated, it's quite low amount of moisture. As a result, dry air does not transport much heat. Warm ocean currents carry large quantities of heat polewards from the tropics. They're constrained, though, by the distribution of land and water. The oceanographers talk about gateways. These are gaps between continents which facilitate the process of moisture, water, of heat rather, being shifted northwards or southwards. Examples would be the North Atlantic Ocean and the Gulf Stream. The circular shape of Antarctica and the cold halo of water, meltwater around it, stops the warm surface ocean currents from reaching the South Pole. So Antarctica remains. This shows the distribution of the currents The Gulf Stream is the most effective because it moves heat from the tropics northwards across the Atlantic and heats up the Arctic Ocean and also Europe. In the Pacific, the Kurashiro current travels across the North Pacific from the Southeast Asia, but it bumps into the meltwater from the glaciers along the south coast of Alaska. And so it gets deflected back westwards or southwards. And so it can't get easily through the Bering Strait, which is quite narrow, and they're rather shallow waters, no more than 50 meters deep. In the southern hemisphere, you see the Antarctic circumpolar current along the south. That is the cold current coming from the melting of the ice sheets in Antarctica and acting as a halo of cold water, which stops surface currents penetrating. So you don't have the same transport of heat to any great extent far south in the southern hemisphere. The primary source of cold, dense Arctic air is in the interior of northeast Siberia. The coldest temperature there is down to about minus 65 in winter. The cold Siberian air mass moves eastwards along three main pathways, each producing distinct ice caps in North America during cold glaciations. This eastward movement is caused by the rotation of the Earth from east to west, and the Arctic air mass is warmed by the Gulf Stream over the North Atlantic, resulting in warmer weather over Western Europe. It absorbs heat from the ocean and also moisture. And this air then cools as it passes over Eastern Europe, and it goes across to Asia, where it stagnates and cools to form the next lot of cold, dense air. This shows the paths. The path one is only used in at certain times. It cuts south from Siberia, round through the Bering Strait, and then south into the Pacific, and then comes ashore in in the southern East British Columbia. Path two takes the cold air into the Yukon, where it meets the warm air coming up from the south, and it has to sit there until it's cooled enough to develop enough density to push the warm air south. And that's how you get the breakout of the cold air into coming south into Canada and south of there. The main path, the most important one, is coming across the Arctic and coming into the Hudson Bay area. And it stagnates in this area here, and it cools, and then it comes south, and it affects primarily Quebec and Ontario. afterwards, the air comes here across the North Atlantic, picks up heat from the Gulf Stream, and also moisture, and it then brings warmer weather and rain to Western Europe, and it gradually cools down as it moves across Europe into Siberia, and in the long run ends up in the source area of the cold air in Siberia. Over oceans, the sources of warm air masses are centered on the zone of intertropical convergence between tropics of Cancer and Capricorn, where the sun is directly overhead twice a year. These are the main sources of the warm ocean currents, as well as the monsoons or typhoons and the rivers of rain. We get rivers of rain coming in from Hawaii and hitting the British Columbia and carrying a tremendous amount of moisture, which is the reason for the flooding in the area adjacent to Vancouver in recent years. On large continents in tropics and subtropics, the main sources of dry subtropical air are the desert areas, such as the Sahara in Africa, the Mojave Desert, and northern Mexico in North America, and the Gobi in Asia and Central Australia. This shows you the concentration of monsoons and typhoons. They occur chiefly in the northern hemisphere, on the east side of continents. It comes from the eastern part of Asia, travels north, and takes a lot of heat northwards with it because of the tremendous amount of moisture that these storms carry. There's some on the west coast of Central America, and another main group that come up here and create trouble along the the east coast of North America. In the south, though, there are relatively few typhoons or hurricanes, and they don't travel very far south. As a result, it's mainly heat transport into the northern region, the northern hemisphere. And this, of course, builds up heat there. Identification of cold areas on land areas. These are best known today from the glaciers remaining from the last ice ages and areas of permafrost. We don't know too much about this complete sequence of cold events on land by looking at sections of soils and deposits. Because when a glacier moves over the surface of the land, it tends to erode the pre-existing material. A reasonable but incomplete record was obtained by plotting all the available dates of cold events on a histogram. This showed that there have been at least 13 cold events starting about 3.6 million years ago. For a more complete record, we have to go to the oceans. When they drilled in ocean cores and examined the sediments, they found they were full of plankton, and this allowed them to have a look at the climate record in the oceans. And they found that it consisted of something like 120 alternating cold periods and warm periods. It turns out when they add actual dating to this, that every four cold events correspond to one glaciation in the last 800,000 years. Earlier on, the spacing is much closer at the alternating layers, but it's not as extreme. This range is not nearly as extreme. So there's a change somewhere about 800,000 years ago, about here. It matches a change in the geomagnetic polarity timescale. This simply tells you the source of the climate data. It's by oxygen isotopes. The shells are for a minute for it. And we get over 100 temperature fluctuations. That is also backed up by geomagnetic polarity. And it tells you simply that there were 23,000 year cycles for glaciation, which lasted for about 90,000 years. And in between, you'll get interglacials of about 10,000 years, separating them. And the 23 cycles, Ka cycles, matches the precession cycle of the Milankovitch curves, and obviously controls it. Previously, these cycles were more frequent, as I showed you, and there's been steady increase in cooling with time. That shows up very clearly on the diagram. Well, if you were moving heat always to the north, you'd end up with boiling water. There's no evidence for that. And we again have to talk to the oceanographers, and we find that the evaporation of water and addition of heat to the air causes the Arctic water to become heavier, and it drops from the bottom of the ocean and then periodically flows out in a cold current here, but it's a deep water, very dense saline flow. And if you move a lot of water down here, you're then going to have to have a return current to keep the ocean flat or horizontal. And that results in a return flow of cold Antarctic water into the North Atlantic periodically. And that seems to be one mechanism for making up for the heat accumulating in the north and then transporting it down south. It cannot go all the way to Antarctica because of that halo of cold water at the bottom here. And in fact, it can go under the halo of cold water, and it does, and it tends to cause a bit of melting of the base of the ice caps, and this can give you the ice breaking away periodically from the Arctic and coast. This simply explains what I've been talking about, and together with the heating of the north, this seems to explain the cold and warm cycles that we see, or in part at any rate. Okay, this one shows you the apparent amount of atmospheric carbon dioxide in the air over time. And you can see that after about the end of the Jurassic, the amount has been dropping steadily. The highest amount was in the Cambrian, just after the appearance of large numbers of animals in the ocean that we see in the Cambrian rocks. These produced great amount of carbon dioxide. The oceans were much bigger at that time, with much smaller land masses, and as a result, a tremendous amount of carbon dioxide was given out, and reached a peak about here. You see a drop after that to here, and that is this part in particular corresponds to a glaciation in South Africa. It's this part here. You can see the temperature. We had a small glaciation in late Ordovician times, which caused quite a bit of reduction in the carbon dioxide. And here you see a long reduction, and it became almost removed from air. Okay, there has been a recovery in temperature, all right, but not so much of the recovery in the carbon dioxide. And with it dropping, that's becoming rather serious. The IPCC, the Intergovernmental Panel on Climate Change, proposed in 1988 that human activities have resulted in increased levels of atmospheric carbon dioxide, causing an increase in global temperatures that overrides all natural causes. Specifically, they assume that the increase began at the start of the Industrial Revolution. It's certainly true that carbon dioxide is a greenhouse gas, but it only affects a small range of the full long-wave radiation emitted by the surface of the Earth. The content of atmospheric carbon dioxide is measured at the summit of Mauna Loa, and since World War II, it's been increasing, and it parallels mean annual air temperature. Although this is certainly not the cause of the climatic changes. Carbon dioxide is an odorless, colorless gas with a molecular weight of 44, compared with the average for air being 29. It therefore sort of settles out in low places such as hollows. All theories involving the formation of a layer in the stratosphere of rock. It is unusual in that it becomes more soluble in water at low temperature, and when the seas warm up, degassing occurs, just the same as the gas that comes out of your glass of pop as it warms up. This can explain the parallel reaction of the gas to the warming temperatures today. As a chemical substance, it has the other property that it can react with other substances, such as calcium ions in the sea, to form calcium carbonate. It does so in all water bodies where there is an abundant supply of calcium ions in the water. The reason for the disappearance of so much carbon dioxide from the atmosphere during these glaciations here were the result of atmospheric CO2 dissolving in the seas and then reacting with the accumulation of calcium ions, which had resulted from weathering over 3 billion years, and they had been stored in the ocean. The sodium ions linked up with chlorine to form your table salt, but the calcium remained waiting for a partner. And as a result, as CO2 dissolved in the water, it reacted with the calcium and formed the big limestone areas that we have today. For example, the Rocky Mountains, which run from Mexico up to the Arctic, the limestones around Ottawa, and well, many more in Europe and Asia. So that was a period in which a great amount of calcium carbonate was deposited. It hadn't been deposited before, and it hasn't been deposited since. But its effect was to take out CO2 from the air. The appearance of numerous marine animals, as I said, resulted in the atmospheric carbon dioxide becoming very high in the Paleozoic. But during the 600 billion year Karoo glaciation during the Carboniferous and Permian periods, it dropped to dangerously low levels, which is never recovered. The atmospheric carbon dioxide rose near the end of the Jurassic period, after which it's been steadily dropping. Each time there's a cold period or glaciation, the carbon dioxide increasingly dissolves in the oceans, where it can react with the calcium to form more limestone. So not all the gas is returned to the atmosphere when the temperature rises. During the last two glaciations, the atmospheric carbon dioxide decreased to within 100 parts per million, the concentration at which plants carry out photosynthesis. This means that if you have too much decarbonization, or putting the carbon dioxide underground, when the next cold period comes along, the atmospheric carbon dioxide will disappear into the ocean, and there won't be enough gas left to allow photosynthesis of plants. If that happens, our food supply is gone, and life on Earth as we know it will end. So that is a rather important finding. Just to show you the IPC, the NASA map for temperature change, comparing two periods of time, where they had enough weather stations in the world, and seeing how far they've changed in that period of time, we find that the Arctic is the area with the greatest change. It's quite high all across here, but not much in the south. To make it worse, if it's supposed to reflect the industrial areas, you'd have to have industry all along the Arctic, moderate industry here, and moderate industry here and here, no industry in China. This doesn't fit. Obviously, that theory doesn't work too well. Again, if you go back to the diagram that we had earlier comparing the temperature and the CO2, you'll find that they're vastly different in the geologic past, and therefore this theory cannot work. Yes, this just tells you the main warming areas are in northern Canada, a lesser warming area in Sahara and the Australian outback. Eastern China and Germany show no obvious warming. Antarctica shows evidence of cooling. Obviously, this disagrees with the IPC, whether we like it or not. We now have some new data coming from Salt Lake City in Utah. There, the Americans have been measuring the solar radiation coming in to the outer surface of the atmosphere using satellites. It shows that the red dots are the summer peaks, which is steadily going up, which corresponds to the warming everybody complains about. But the winter cold reached a peak in 2020 and now is dropping. And I think if it keeps on going like that, it indicates that the 23K peak of warming ended about 2020. At the moment, you're getting heating in summer, continuous heating, but in winter, you're getting temperatures getting colder at the surface. So we're headed towards another glaciation. Why do these behave differently? Well, the source area for the cold air mass is in Siberia. And that is at a latitude where you have one summer and one winter. The warm air masses come in from the subtropics, where you have two peaks of heat in the summer period or in the year. And as a result, it takes time for the tilt of the Earth to change enough to have the air cooling down in the source area of the tropical, subtropical air masses. We'll see whether this continues, but that is the present situation. This is just simply tells you that the summer values continue to increase, indicating that the subtropical air mass is still warming. This will continue until the position of the overhead sun in its source area moves south. And after that, that will decrease. So we have a situation where the warm and the cold sources are out of phase. And this is something we hadn't realized before, that this will be modified by local factors, such as ENSO and so on. It is evident these changes measured by satellite match the evidence of timing and much more extreme weather in Canada that occurred in the last 3 years. In the Rogers Pass, we've had an increase in snow avalanches, 7 additional ones, in spite of only being about a total of about 45 previously crossing the road. And you've had extreme flooding events across Canada, drought in the boreal forest and prairies, and as a result, you've got spectacular fires, many more tornadoes over much of eastern and western Canada, and record summer temperatures, and similar changes are occurring throughout the world. This was an abrupt change about 2020. And in Antarctica, the 2018, they measured the coldest temperatures on Earth that have been measured. That's minus 98. And they are the opposite end of the Earth, and that would be the coldest period, corresponding to the warmest in the northern hemisphere. Assuming that the next two 25 Ka climatic cycles evolve as they did in the last glaciation, a good idea of the results for Canada, we are likely to be those that developed about 65 that's 10,000 years before the present. And the next slide, I think, shows you the areas that were under the snow, under the ice at that time, that all along the mountains, the Rocky Mountains, into southern BC, a big area in Keewatin, and a very big one in the east, which corresponds to the effect of the cold air coming down here and then bringing snow to the mountains in Quebec, and they extended south even to Kansas. And you'll notice that sea level drops to make up for the ice that's been loaded onto the land, and the Northwest Passage is no longer there. And Greenland is connected up to Baffin Island and the mainland. That's a long way ahead of our present day. We don't have to worry about it, but maybe our offspring may have to adjust to it sooner or later. While there's plenty of time before the glaciers cause us to have to move about to adjust to the land that is hospitable. Our ancestors had to, excuse me, had to survive two such glaciations in the past, although the number surviving were quite low. The presently expanding world population will have to adjust to changing environments. This will undoubtedly involve reductions in the current population of Canada instead of the current migration to this country. Immigrants to Canada are jumping out of the frying pan into a fire, so to speak, in the long term. This will be a problem throughout the world. This shows you the tremendous growth since deglaciation and about World War II. And we've got increased something like sevenfold or eightfold in numbers. And that is going to cause problems, obvious problems. In fact, it is. What about future power sources? Well, electric grids seem to be very popular among the people who are concerned about carbon dioxide. Overhead cables are very susceptible to collapse due to icing up. They also probably don't stand up too well to very strong winds, and underground cables break in permafrost areas. The current hydrological hydroelectric reservoirs will be covered in ice. They're extremely expensive to construct or everything connected with this. In Europe, they suddenly realizing that although they're going to electric cars, they have to completely rebuild the electric grids to carry enough juice to cope. And that's extremely expensive. And for a country like Canada, that is trouble. Solar power, heavy snowfalls and bad weather, or it will be problems, and it's not much use in the Arctic. Wind power, that is unreliable, given extreme winds. Atomic power plants, these should only be constructed in areas least likely to be glaciated, owing to the problem of disposal of radioactive waste. If the waste gets run over by a glacier, we're liable to end up with radioactive glacial sediments. Oil and gas will have to be the backup means of producing energy, and they will require pipelines in areas not susceptible to glaciation. Coastal wave energy, if the sea level remains still, that's okay, but if it starts dropping, you're going to have problems with that. Coal wood at the last resort. This is just emphasizing the carbon dioxide photosynthesis in light. And the photosynthesis requires chlorophyll in vegetation, requires sunlight, moisture, and of course, carbon dioxide. If you have depletion of carbon dioxide in cold events, and it falls too low, we're going to be in big trouble. We've been very, very close in the last two glaciations to causing trouble. In fact, it may have caused a bit of trouble for plants. Presently, it's degassing from the warming ocean water, but we're shoving it underground to achieve net zero carbon dioxide. So when the next cold event occurs, the atmospheric carbon dioxide may fall below the level required for photosynthesis. The plants die off, and so do we. And we'll end up with a barren land surface, a bit like the other planets. Climate change has an enormous effect on economics. Although mankind may like to think they control climate, they actually have to adjust to it. That's reality. An enormous amount of money has been spent on decarbonization when the cause changes are different. And the carbon tax should be abolished. That's created an awful lot of trouble. For example, if a farmer has to pay tax on his seeds, his fertilizer, and fuel, when he sells the goods, the result to the railway company, he has to pay tax on that. The railway company sells it to the miller, and they have to pay tax, and then it has to be packeted. The flour has to be packeted, and more money goes to the government. And then, of course, you buy it in a shop, and it's gone up again. So that is why we've partly why we've had inflation. Carbon dioxide is essential for life, so it should not be feared. It is necessary to adapt to the changes as if as they occur, if we are to survive successfully. Changing to electricity as the main power source will be too expensive. It will create its own problems, especially for large countries with a population spread out over long distances. Oil and gas are going to be of continuing importance, partly to have a means of moving around, making repairs during power failures. If you've only got electric vehicles, how do you go out and repair the lines? Pipelines to get hydrocarbons to where they need are essential. The best way to cope with the energy problems is to use all resources together. An electric grid is subject to hacking. That's always a problem. Adaptation to climatic changes will be essential. Fire-resistant buildings, for example. Insurance costs are going to be high and problematic with climate change, and it's important to realize that changing sea levels and shoreline will be part of the problems we shall have to adjust to. When the sea level goes down, the rivers start cutting back, and so you have problems with your docks. You have problems with your landscape because of the erosion. So that's the talk.
Are you predicting cooling between now and 2050 or 2100, or does anybody know short term what's going to happen?
Okay, we have two competing processes. One is winter cooling, the other is summer warming. Now, this occurred at the end of the last interglacial for a short time, and then then the summer temperature started dropping. And once the tilt of the Earth has changed enough to cause the areas in the subtropics to cool, then you have two lots of cooling operating, and that's when it will the temperatures really will drop.
Okay, I'm trying to find out though what you think about the timing of that. Is this 50 years?
We don't know. We don't have good enough timing on the end of the last interglaciation. This is a time of recording and learning. We've had our work cut out to get this far because we've been in a period in which conditions have been relatively stable. So the historic period has been one in which we haven't really seen the worst of it. And we are going to be making history.
All right, very good. I wanted to mention that the slides for this presentation, there'll be a link in the show description so people can look at your slides. And then you have 2 papers that came out this year, right? And PDFs of those papers, I'll put links to those also from the show description so people can go and read those. But do you want to talk about the papers or mention what they're about at all?
The one paper this talk essentially deals with. The section on the photosynthesis and the continuation of life is the other paper. There is another one earlier, which well, there are several actually. One looks at the history of climate from the start of the Earth. And that one gives you a better idea of what has been happening. CO2 was not an original component of the atmosphere. It was more sulfur dioxide, H2S. And then after a long period of that, a small amount of carbon dioxide developed from methane. But oxygen was the next main component, and that's how you formed your iron ores. And then it was not until the arrival of the marine animals in large numbers, much larger seas than we have today, that you produce enough carbon dioxide that you pushed up the CO2 content of the air. Before then, we didn't have really a source. And that helped the plants that have been around for quite a long time and produce the oxygen that resulted in your iron ores. But so you'd have to read the paper to see. Do you know ResearchGate?
I do, yeah. Look it up there.
Look up Stuart Harris on that, and it will tell you my recent papers. With little E1 dealing with the circulation of the air around the Arctic has had over 1,000 reads, and some of the others are up in the 500-600 read range. And this last week, students were preparing for exams, and there were over 500 reads of my papers in a week.
Excellent.
So, it is catching on, and I'm getting thanks from various people for daring to rock the boat. But it actually started because I've been hiking with, I belong to a hiking club, and I've been hiking with the CEO, ex-CEO of one of the oil companies. He was grumbling away about the tax and so on. So I said after I just finished the Permafrost work, I said I'd have a look at it because it does tie in with the permafrost. Because permafrost is generated by the cold. And as soon as I found the snags with it, he was much happier. And he died about 2 years ago. And the first of my papers, in which I laid out this, it was published 2 weeks before he died. He died a happy man.
Okay.
So,
All right. I'll definitely look up those papers. I do have one final question. I don't know if you have been watching what happened just in recent months. There's been a spike of warmth that shows up in the UAH data. Roy Spencer has been showing a spike in warmth very recently, and people are speculating maybe it has something to do with a volcano putting a lot of water vapor in the air. Do you have any opinion on that spike?
water vapor, if you put it into the air, it falls to the ground fairly soon after, somewhere. So I'm not sure that is that critical compared with the movement of heat. Geothermal heat is only a fraction of the heat coming to the surface. And in a localized area, it can be important. But in general, if you think of the quantity of solar radiation hitting the Earth every day, and the Earth, remember, is spinning. So just because it's dark for you, somebody else is getting sunburned. So the other possible, several other possible sources. One is to have a giant asteroid hit the Earth, and that has happened. But on the other hand, although it creates havoc for a short time, the actual energy applied to the Earth is still small as a percentage of the solar, compared with the solar radiation, which is continuous. Now, the solar radiation, when you look at my paper on the history of climate, you'll find it was only 75% as high at the origin of the Earth. It's been steadily increasing. They think this is a red star, and red stars gradually expand, throwing out more and more heat, and they gobble up the three nearest planets before they disintegrate. They've had a photograph of one, the astronomers have come up with a photograph of one of these red stars swallowing up a planet. So it isn't that it doesn't happen. Now, whether they've got it right, we are a red planet or not, I don't know. But if you are asking, if you're asking about the future for species, if it continues to warm up, there'll have to be a change in the species. that our bodies depend on chemical reactions, thousands of them. And when you change the temperature with the chemical reactions, they either speed up or slow down. And this messes up the equilibrium in the animal or the plant. And only something that has evolved to adjust to these new conditions will survive. And this is why we've been losing species steadily since the Jurassic. And we're an adjustment to the cold compared with, a dinosaur would be in big trouble at the temperatures we've got.
Do you think there's actually more species diversity back then than now?
No. What you do is you keep changing with the climate change. And that's why species tend to come and go. Unless they're like, say, a shark, which can go deep in the ocean if it gets too hot up above. If they've got a swim bladder and they can go deep, then they can adjust. And they've been around since the Paleozoic. The idea that is a technique of adjusting to different temperature changes and keeping on going. But if you're like us, it's not so easy. Once you've got down to your bikini, you've got a problem.
Very interesting. So the sharks that are swimming around now might be a similar species as sharks that were swimming around a long time ago.
They are. They are. But you see, the dinosaurs, they had a couple of problems, I think. One is that they were very large, so they needed an awful lot of food. And they lived in a semi-arid climate. The vegetation was iffy. And they had big floods. They also had fairly dry areas too. And if you look at the length of time each species lasted, it's fairly short. This is what they're finding out now here in Alberta. And they had different species in China. There, the first bird-like fossils are found. And the dinosaurs there tended to be feathered.
Yeah, I've heard that story off and on for many years, but dinosaurs, some of them really did have feathers, right?
Yes, they did. And eggs, and so your birds that you feed at your bird table are young dinosaurs. The offspring thereof but have adjusted to a climate change.
Very, very interesting. Okay. Any other points you'd like to make before we go ahead and finish this one up?
I don't think so. I think you've got enough here to cope. It is rather ironic that the people pushing the CO2 theory in the government are on the limestone that was formed, and the building is formed of the same limestone. If you see,
never thought of it that way. Very good.
But as you go through, you start finding anomalies of this sort. And the abandonment of the idea of the Milankovitch spacing of the Earth and movement of the Earth and the Sun and so on has been almost abandoned since about 1950 in favor of this other. This other, I think, if you want to really know the causes, the government in the 70s and 80s was cutting down on research in physical sciences. It closed terrain sciences division. It stopped measuring the sea level around the Arctic. Sea gauges were abandoned and so on. And I think scientists were getting a bit concerned that too much money was being put into the social sciences. And I suspect that they felt that this was a good excuse to, well, I think you see my train of thought.
Absolutely. Maybe I do have one more question then. If you agree that the Earth has warmed maybe 1 degree centigrade since the late 1800s or so, what percent of that do you think may have been caused by humans?
Very little. You'll know a lot more when you see the effect or lack of it on the CO2 increase at Mauna Loa from all these forest fires that have been taking place. If these do not cause a blip in that, then the chances are that your industry has not contributed very much. You see, if you think about it, I don't know what latitude you live at, but
it's about 45, right about 45.
45. So you would have almost double the incoming radiation that we have here at 54. I lived in Guyana, and I know how much radiation you get in the tropics, and it's more than double. And in Tibet, I did a lot of work in Tibet, and the radiation there is horrific coming in from the sun. So that if you live at higher latitude, you don't realize just how much energy comes in. It's enormous.
Just because you're living so high up that there's not much atmosphere stopping the sun, huh?
Well,
a big part of it?
No, because the angle of the Earth, the rays coming in are coming in on at a lower angle. You've got the same density of radiation coming across. When it hits at right angle, you've got the maximum. And then as you alter this angle, the amount decreases.
Yep.
So that even at 40, you're still only halfway towards the equator.
Okay, so maybe I should ask one more final question. This will be the final one. Do you believe that atmospheric CO2 has risen from maybe 280 ppm to 420 ppm since the 1800s? And if you believe that, what percent of that do you think was caused by humans?
Very little, I think. Very little. Because you've had a lot of vegetation, and vegetation has been sequestering carbon. And the biggest problem has come probably in deforestation. And that alters the surface temperature quite a lot. But I don't think it's. We're working on it, given the numbers of people.
Okay. All right. Very good. All right. With that, I will let you go. But thank you very much. I really enjoyed hearing from you, and I hope to do this again.